This demonstration of the Ext Chart program is meant to showcase the program's ability to compute with integral homology classes. To find a good example of this, we turn to the homotopy fixed point spectral sequence, starting with the homotopy groups of the C2 equivariant version of complex K-theory and converging to the homotopy groups of real K-theory. The E2 page of the spectral sequence is presented as the quotient of a polynomial algebra. So I'm going to study a slice of this by constructing a new polynomial spectral sequence. The two generators are given in degrees 1, 1, called eta, and in 4, 0, called beta squared. Neither of these classes are truncated, so I'm just going to stick in large numbers here so we get a picture. And you see the picture that Ext Chart has drawn here is a picture of a polynomial algebra. So these squares are the terms eta, eta squared, eta cubed, beta squared, and there's some mixed terms out here. Now, the E2 page of the spectral sequence isn't just a polynomial algebra, it's a polynomial algebra plus a relation. One way to inform Ext Chart of this relation is to introduce a bounding class or a coning class. So that's what I'm going to do. I'm going to stick a class in 2, 0. I'm going to give it a name, the cone on twice eta. So turning to the first page, I can insert a differential here, which will have the effect of sending the cone on twice eta, the class representing the cone on twice eta, to just the class twice eta. I also have to inform Ext Chart that beta squared does not play the role of a coning class, and so I have to say that this relation holds. But now that Ext Chart knows about those two relations, it can calculate what we mean everywhere else. When I turn the page, I see something slightly better. So if I inspect these classes now, here's the class 1, here's the class beta squared, which is still a torsion-free class, very good. And I also see that my class eta has become order 2. And similarly, all of these mixed products, because they contain etas, are also order 2. On the third page, the last differential in this spectral sequence is a differential sending beta squared to eta cubed. And again, using the Leibniz rule, if I tell Ext Chart what the generators of this page are, it can figure out the rest. And when I turn the page, I see the picture that I'm meant to. And more than that, Ext Chart recalls the names of all of these classes that have survived. So sure enough, 1, eta, and eta squared are the classes that survive here. And not only does Ext Chart know that this class belongs to beta squared, but it knows that this class is in fact twice beta squared. Whereas here, it understands that the surviving class is just beta squared squared. So it keeps track of the orders and what belongs to what.